So we're going to continue our work with exponential functions by looking at slight variation on what we've seen so far. We're going to look at some examples where f of x is equal to a times b to the x, where a and b are constants. So we're introducing this scaling factor of a, you might call it, and we're going to see how that affects the shape of a graph. The value of b, don't worry about the fine print here. We always take b to be positive. Negative values of b really don't make sense. They're not defined for all values of x, so we never deal with negative b. And b equals 1 is just boring, so we always say b is not equal to 1. The important thing to note here is the effect of a on the y-intercept. If we plug in 0 for x, we get a times b to the 0, which is a times 1, or a. In other words, the y-intercept for this type of function is going to be 0a. So we see the effect of a in the position of the y-intercept. So let's go ahead and do some graphs of functions of this type. Our first example is 5 times 3 to the x. This is actually the example I used in the introduction video where I didn't tell you right away what the function was. We just plotted some points. So we kind of already know what the shape is. But now we can see it's of that form, a times b to the x. The base is greater than 1. So that really, it's the 3 more than anything that determines the shape of this graph. We know because the base is greater than 1, the shape of such an exponential function is going to be like so, rising up from close to the x-axis and then taking off when x is very, very positive. And yet this is slightly different from 3 to the x because the y-intercept for this function when x is equal to 0 is going to be 5 times 3 to the 0, 5 times 1, or 5. So 0, 5 is the y-intercept. So the 5 changes all the values on the graph, but we only indicate it in our picture with the y-intercept here. The shape of the graph is just very, very, very similar to the shape of 3 to the x being graphed all by itself. Let's look at number 2 here. Now, here we have negative 2 times 1.25 to the x. So again, we have a base greater than 1. But the minus sign here in front tells us that we will have to reflect through the x-axis. So I'm going to draw my x-axis up a little higher. Y. And imagine taking this shape of number 1 and reflecting that shape through the x-axis. What we're going to have is we're going to start out below the x-axis and curve downward from that. We still have the x-axis as a horizontal asymptote. That's true for both 1 and 2. And again, this graph is below the x-axis in 2 because of the reflection through the x-axis. My y-intercept, when x is equal to 0, is going to be at negative 2, same as that coefficient value, negative 2. And number 3, we're looking at 10 times 0.25 to the x. Notice that the base here is between 0 and 1, so that means we have to use our other fundamental shape, or slight variation on the exponential graph. We're going to use that shape where we start out high above the x-axis and slowly decrease until we approach the x-axis when x is positive. X, y. And the y-intercept here when x is equal to 0. We get 10 times 0.25 to the 0. 10 times 1 is 10. So that y-intercept is 0, 10. And we have another base here that's less than 1, between 0 and 1. And we also have a situation in number 4 where we have to reflect through the x-axis. So I'm going to take the shape that we see in 3, and I'm going to reflect through the x-axis. So my y-intercept is actually going to be on the negative portion of the y-axis. This portion of the graph, when we reflect through the x, will become a piece coming up from below. And then instead of approaching the x-axis from above, we're going to approach the x-axis from below. And my y-intercept when x is 0 here will be -3. You can either plug in or use that value of a to label the y-intercept. Okay, let's look at some more examples. Okay, number 5, 2 times 1.8 to the x minus 5. We're back to b being greater than 1. And we also here have a vertical shift of down by 5 units. We're going to shift downward. So when I do a vertical shift, either up or down, the horizontal asymptote shifts with the graph. So I'm going to have to show the new position of the horizontal asymptote. It started at the x-axis. It's going to shift down 5 units along with the graph, so it will end up 5 units below. So I draw this dashed line at y equals -5. Now I'm going to add to my graph this base greater than 1 shape of the exponential curve. That's a curve that starts out along the horizontal asymptote and turns upward as we move to the right. So I have to start out along my horizontal asymptote, cross the y-axis, turn upward, rising, and my y-intercept value here, now it's going to be affected by the vertical shift. So the 2 value would have been my y-intercept value without the vertical shift. When I shift down 5, I'm going to get 2 minus 5, or -3. You can also just plug in. So always realize you can plug in to compute the y-intercept. Plug in x equals 0. I get 2 times 1.8 to the 0 is 1. 2 times -5 is -3. So that's 0, -3. And there's x, y-axis. And the x-intercept we don't have to calculate at this point. We're going to figure out how to find these x-intercepts later in the chapter. So eventually we'll need them, but not right now. Okay, next example, number 6. What's going on here? We got inside the exponent, I see this x minus 2. That's telling me we have a horizontal shift. And because it's minus, that's to the right by 2. So I'm going that way by 2 units. The minus sign also tells me that I have to reflect through the x-axis. And I'm starting out with a base that's greater than 1. Now, it's okay to draw some preliminary graphs if that's helpful for you. So for instance, here, I might want to think, okay, I want to start out with y equals 3 to the x. Okay. And then I'm going to shift this horizontally, and I'm going to reflect through the x-axis. Now the horizontal shift won't be, like the shape will still be pretty much the same, but it's the reflection through the x-axis that you got to make sure we indicate clearly here. So my graph is going to end up below the x-axis in that kind of a shape. The horizontal shift does not change the position of the horizontal asymptote. It just moves sideways and stays in its position. When we reflect through the x-axis, the horizontal asymptote doesn't move either. So notice that the horizontal asymptote just stays on the x-axis here. And I want to label my y-intercept. If I plug in f of 0, that's negative 4 times 3 to the 0 minus 2. That's negative 4 times 3. Now I actually get 3 to the negative 2, which is negative 4 times 1/9, or negative 4/9. So the y-intercept is not at negative 4 because it's affected, you know, that negative 4 point moved with the horizontal shift. So the new y-intercept is 0, negative 4/9, which you can always get by just plugging 0 in for x into the function. And if you want, because we shifted 2 to the right, it's kind of like the old y-intercept before the horizontal shift is sitting here to, you know, at x equals 2, and the coordinates at that point should turn out to be 2, negative 4, with the y coordinate matching the a coefficient, negative 4. Now you don't have to plot that point, and so that's not required, but that's just to kind of indicate a little bit of how really the position of this graph did change through the horizontal shift. We're just not noting those details so much as long as we plot the correct y-intercept. Okay, number 7. Number 7 is of that form where I like to rewrite it as negative 1/3, 2.5 to the x plus 2. And that way we can see that there's a vertical shift of up to. We can also see that there's a reflection through the x-axis. And here I may even do this one in a couple steps. I may start out, let's just start out with the basic graph. The base is greater than 1, so I start out with this shape. Y equals 2.5 to the x, with the x-axis being the horizontal asymptote. I then have to reflect through the x-axis. So this is like the y equals negative 1/3, 2.5 to the x. And then I have to do my vertical shift of up to get the final graph. So when I shift vertically, the horizontal asymptote is going to shift also vertically. So my horizontal asymptote will shift up to y equals 2. And so I'm taking this shape of a graph, which let's extend my axis here. So I'm starting out close to the horizontal asymptote, and then I start dipping as I move to the right. And I want to label my y-intercept. My y-intercept value is going to be what I get when x is equal to 0. When x is equal to 0, I get 2.5 to the 0 is 1. I end up with 2 minus 1/3 to the 1 power. 2 minus 1/3 is going to be 5/3. That's 0, 5/3. And let me just write out that calculation here. F of 0 is 2 minus 1/3 times 2.5 to the 0 is 2 minus 1/3 times 1. That's 2 minus 1/3, or 6/3 minus 1/3 is 5/3. That's the same as 1 and 2/3. It's my y-intercept. X-intercept, we don't need to worry about. The y equals to horizontal asymptote must be labeled in this picture. And now, so we got 5 in blue, 6 in blue, 7 in blue. We have one more graph to draw here. And number 8 has a base between 0 and 1. And I see that I also got a vertical shift of up 1 unit. So if I start out with my just basic graph of 0.8 to the x, 0.8 to the x is going to come down from above and approach the x-axis when x is positive. And I'm not doing any reflecting here. Again, the 0.4 is just going to slightly change the shape, change the y-intercept, but I have to do a vertical shift up 1 unit. Whenever we do a vertical shift, the horizontal asymptote is going to shift. So shift up 1 unit. So at y equals 1. And the shape of my graph is going to come down from above and approach that horizontal asymptote. So it's going to have the same basic shape as 0.8 to the x, but just lift it up a unit. And then the value of my y-intercept, f of 0, is 0.4, 0.8 to the 0 plus 1 is 0.4 times 1 plus 1 is going to be 1.4. That's 0, 1.4 is the y-intercept. And so there, overlapping my statement of the problem a little bit, is our fourth graph on this page. I have one more example I want to include here that is a kind of problem that occurs on the homework. The graph of an exponential function passes through the points 224 and -1, 3. Find a formula for the function. And so what we need to do is we need to find values of a and b for f of x equals a times b to the x. And to do that, we're going to use the fact that we know if the point 224 is on the graph, we know f of 2 is 24, and we know f of negative 1 is 3. And now what I want to do, though, is I want to take this function notation and make use of this a times b to the x form. So the f of 2 I can rewrite as a times b to the 2, as if I plugged in 2 for x. That's got to equal 24. The f of negative 1 is a times b to the negative 1, as if I plugged in negative 1 for x, and that's got to equal to 3. And what I end up with here is what we call a system of equations. I have two equations and two unknowns, we say sometimes. And so it's a system of equations. I have to solve for a and b. I'm just going to maybe call these equation 1 and equation 2. So I'm going to just recopy them here. Equation 1 is ab squared equals 24. I don't need the parentheses. Equation 2 is ab to the negative 1 equals 3. And now there are different techniques you can use to solve, but substitution is probably the most useful technique for solving a system. I'm going to try to do a substitution here. I'm going to take one of these equations and isolate one of the variables. Now I can rewrite 2 as a times 1 over b equals 3, or a over b equals 3. And I can go ahead and, because I have a fraction here, I could multiply both sides by b. I could take b times a over b equals b times 3, and that gives me a equals 3b. Now I cleared denominators there, but I also have a nice result here in that a is solved for, a is isolated. So I can use this to make a substitution in the other equation. I'm just going to recopy this here. ab squared equals 24. And I'm going to replace the a using this other equation information. A can be replaced with 3b. 3b goes in place of a times b squared equals 24. So by making that substitution, substitute 3b in for the a. By making that substitution, I get an equation with one variable, 3b to the third equals 24, that I can now solve for b. Divide both sides by 3. b cubed equals 8. And I can take cube roots to solve for b. b will be the cube root of 8. And that just happens to come out real nice here because the cube root of 8 is 2. Now I have a value for b. We still need a. So I'm going to use my a equals 3b equation from back here to plug in my value for b. A is 3 times 2, so a is 6. I have a value for b. I have a value for a. And now I can write down the formula for the function, because the problem asks us to write down this formula. F of x is, instead of ab to the x, I can write 6 times 2 to the x. And there's my answer. You can check this by plugging in each of the two given points. Both of the given points should fit this function, and if you've checked that, they do. We got it. There's our formula for the function in that exercise. Just going to rewrite it back up here. What we got was f of x equals 6 times 2 to the x. That was our answer.